I was talking with my dad a while back, and he shared with me a math problem that his 10th grade geometry teacher gave to their class. The problem was a conjecture, and for any student who could provide a sound proof for the conjecture, the teacher would guarantee them an A in the course. Obviously, I became interested in the problem and played around with it. In this video, I'll present my investigation into the problem. First, I'll describe the original problem. Then I'll discuss counterexamples. Yep, turns out the original conjecture is actually false. Finally, I'll modify the conjecture slightly by ignoring those specific situations which lead to the counterexamples and outline a proof for the modified conjecture. Okay, so the original problem goes like this. Given 4 points on a plane, prove that a square can be constructed by intersecting lines that pass through those points. Again, start with any 4 points on a plane. Then draw lines passing through those points in such a way that when the lines intersect, they form a square. The task then is to prove that this is always possible to do, no matter what 4 points you start with. Now, I want to emphasize a requirement that is implied but wasn't stated explicitly. Each of the 4 points should be paired off and matched up with one of the 4 intersecting lines, and it has to lie on it. Otherwise, we could end up with silly trivial squares that don't jive with the spirit of the original problem. For example, if we just take 2 of the 4 points and consider them as opposite corners of a square, leaving the other 2 points alone, that wouldn't be in the spirit of what we're trying to do here, hence the stated requirement. Okay, so now that the problem's been described, let's look at a counterexample. But, in order to do that, first we need to recall how to construct an orthocenter, one of the points of concurrency for a triangle. Starting with the triangle, draw the altitudes, the lines that pass through the vertices and are perpendicular to the opposite sides. The 3 altitudes of a triangle meet at a single point. That point is the orthocenter for the triangle. If the 4 initial points make up the 3 vertices of a triangle along with its orthocenter, and in every orthogonal segment pair the 2 segments are not congruent, then those 4 points constitute a counterexample to the original problem. Again, if the 4 points form a triangle with its orthocenter, and in each orthogonal segment pair the 2 segments are not congruent, then there will be no way to form a square from lines passing through those points as described earlier. So why is that? Well, notice by the requirements given for the line constructions, for the 4 lines, let's call them L1, L2, L3, and L4. In order for a square to be constructed, we need 2 pairs of parallel lines so that it's ensured the opposite sides of the square are parallel. Without loss of generality, we'll say L1 is parallel to L2 and L3 is parallel to L4. Also, the parallel line pairs have to be perpendicular to each other, so it's ensured the square's corners are each at right angles. Finally, to ensure the square's side lengths are the same, the distance between L1 and L2 needs to be the same as the distance between L3 and L4. So, no matter where we place the lines on the plane, these conditions need to be met in order to construct a square. Well, if our 4 points form a triangle with its orthocenter, and in each orthogonal segment pair, the 2 segments have different lengths, then we end up being forced into a situation where the distance between L1 and L2 is the absolute value of the sine of some angle theta times one of the orthogonal segment pair's segment lengths, and the distance between L3 and L4 is the absolute value of the sine of that same angle theta times the other segment length from that same orthogonal segment pair. Since those 2 lengths are different for our counterexample, no matter which pair we pick, we won't ever end up with a situation where we have a square, since its side lengths won't ever be equal. As a side note, if the 4 points form a triangle with its orthocenter but there is an orthogonal segment pair of congruent segments, then it's very easy to construct a square from those points. Okay, So now that the counterexamples have been discussed, we can modify the original conjecture so as to exclude those specific counterexamples, and it turns out that this modified conjecture is actually true. In other words, if there are 4 points on a plane, such that those 4 points don't make up the vertices of a triangle with its orthocenter having each pair of orthogonal segments being non-congruent segment pairs, then it is possible to construct a square from the intersecting lines as described earlier. So let's look at why that is. I've already discussed that it's possible and very easy to construct a square if the 4 points do make up a triangle with its orthocenter and there is an orthogonal segment pair of congruent segments. Now let's assume the 4 points don't make up the vertices of a triangle with its orthocenter. We'll label the points A, B, C, and D in such a way that segment AB is not orthogonal with segment CD, which we can ensure is possible in this case. That is, the angle alpha between the two segments AB and CD is not pi over 2. As a side note, we'll also consider alpha to be 0 when segments AB and CD are parallel. Draw parallel lines L1 and L2 protruding from points A and B, and parallel lines L3 and L4 protruding from points C and D, with L1 and L2 being perpendicular to L3 and L4. Then if the angle between segment AB and L1 is theta, then the width of the rectangle formed is the distance between L1 and L2 and is given by the length of segment AB times the absolute value of the sine of theta. And the length of the rectangle formed is the distance between L3 and L4 and is given by the length of segment CD times the absolute value of the cosine of theta plus alpha. If we turn the difference between the rectangle's width and its length into a function of this angle theta, then we can vary the angle to end up with a negative value for the function at one input and sweep this angle to end up with a positive value for the function at another input. In other words, this function gives us a rectangle that's longer than its width at one input, and the function gives us another rectangle that's wider than its length at a different input. And since this function is continuous on that closed interval, the intermediate value theorem, specifically Bolzano's original version, guarantees there is some angle input where the function, i.e. this difference, is 0. Hence the length and width are the same at that point, and we know it's a square because the length and width aren't ever both simultaneously 0. So, overall a pretty good problem for a 10th grade geometry class, yeah?